the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant for linear algebra students who are going through Cramer's rule, and you should have already actually learned Cramer's rule at this point. We're going to do a little side topic which will justify why we had to use cofactors in the last video. And this is mainly to help us find the inverse of a given invertible matrix via what's called the adjoint. Now, my little concept note here that I kind of mentioned last video is that we'll continue working with this sadly inefficient Cramer's rule by developing a way to directly compute the inverse of a matrix, but note, despite Cramer's rule being a hopelessly inefficient algorithm, it is still theoretically important. Now, I did mention the word adjoint, so what the heck is that? We're going to define the adjoint of a square matrix A to be the following. That's just noted as ADJ of A. That means the adjoint of A, and it's an n by n matrix. However, the entries should look somewhat familiar, and if you're astute and really paying attention, it should also look really weird. These C sub ij's here, like C sub 1, 1 and C sub 2, 1 and so on and so forth, these are the cofactors that we talked about in the previous video and in our introduction to determinants. However, what looks weird or should look weird about them is that normally you would say this is the first row, first column, and then this would be the first row, second column, but notice that's not how they're written. This is what makes this matrix really weird, is that those entries have actually been swapped rows for columns. That is, this first column here, C11, C12, all the way to C1n should, in our opinion, be the first row. So this is like the transpose of a matrix. However, we need it in this format, not the transpose format. So we need it in this format right here. And like I said down here, Cij is the ijth cofactor of A. My little warning at the bottom, the switching of the indices in this definition is totally deliberate. You need that. So that is the definition of the adjoint for the matrix A. That simple little definition, or not so simple little definition, brings us to the inverse via the adjoint. Let A be an invertible n by n matrix, then A inverse actually ends up being 1 over the determinant of A, which should look somewhat familiar, times the adjoint matrix of A. And if you think about that very simple definition or theorem, actually, it seems very, very enticing. Like, oh man, that'll make finding inverse matrices much easier. Well, not so fast. Because think about it, you're taking the determinant and you're taking its reciprocal, and then you're multiplying it by a matrix whose entries are cofactors for the matrix A. And remember, cofactors are the minors, which are the determinants of the submatrices by removing rows and columns, times some plus or minus sign depending upon where those minors occur. So the punchline is that this requires a lot of determinant computation. We'll still go ahead and do it, but I just want to give you a heads up that that is the reason why this is not such an advantageous way to compute the inverse. But to see it in action is actually to make sense of at least what this theorem is saying and what the adjoint matrix of A looks like. So let's go ahead and find A inverse via the adjoint here. Now, the first thing you should do is really compute the determinant of A because you need that according to the theorem. However, because of the way I want to organize my work, I'll actually write the cofactors first. And when I write the cofactors, I'm going to do it this way. Notice the way I've written it, it looks like it should be in a matrix. It's not, but it looks like it should be in a matrix. Also, it follows what we're very much used to. Row 1, column 1, row 1, column 2, row 1, column 3, and then row 2, column 1, column 2, column 3, and so on and so forth. So this is how we would normally like things written as far as how the indices work, but we'll compute these cofactors and then we'll go back and take the transpose of what this matrix looks like. It's not really a matrix, but we'll take the transpose of this in the end. Remember, the cofactors are going to be -1 to the sum of the indices times the minor of that 1, 1 entry. And the minor of the 1, 1 entry just means take the determinant if you remove row 1 and column 1. Likewise, C12 is going to be -1 to the 1 plus 2 power times the minor of the 1, 2 entry. Now, you can obviously see what's happening here with the negatives, right? It's negative if the sum of the indices is odd. It's positive if the sum of the indices is even. So if you don't mind, I'm going to actually just mark that in here. All right, we have that filled in, and I'll also write in the minors. Now, before I actually write down all the mathematics in the background that's occurring, just note, your other option to find the inverse here is to augment this matrix with the identity matrix and then just use row reduction techniques to get that matrix A to become the identity matrix, and therefore the augmented matrix I will become A inverse. That is not only very familiar to us, but actually computationally less expensive. So what I'm showing you here, while it is kind of cool, it is actually a little more costly in terms of computations because of the number of determinants we have to take. But some people still like it. So let's see. We get this for our first minor, actually our first cofactor. Now what I'm going to do is just go ahead and barrel through and do the rest. All right, we get down to there. Those are all of our cofactors. And let's go ahead and compute the determinant of A. So again, we did all that work. We still have to compute the determinant of A because this theorem requires 1 over the determinant of A times the adjoint of A. Well, the determinant of A, let's see. Actually, maybe I'll write the adjoint of A first because it's easier for us to see right now. The adjoint of A is going to take the transpose of what you're looking at right here. So this very first column will become our first row in the adjoint. And the second column will become the second row of the adjoint. And finally, the third column becomes the third row of the adjoint. So that's our adjoint right there. All I need now is something very simple for us to compute, which is the determinant, which we actually have done. Believe it or not, this is from a different problem. In the last video, we dealt with this matrix right here as the coefficient matrix for that system. And so we did all of that work already, and we found the determinant of that matrix to be 10. So that's what I'm going to use in our work right now. So A inverse is 1 over the determinant of A times the adjoint of A. And if you want to, you could distribute that 1/10 inside. Although, honestly, I would probably have left the 1/10 on the outside. You can double check that this is actually A inverse because we have already solved a system with this as the coefficient matrix, this being this A right here. The system we solved was this system right here. Our right-hand side vector was a -3, 1, 1, and we got a solution of -1, 1/2, 3. So what I'm going to do is just multiply B by the A inverse we just found to see if it becomes this -1, 1/2, 3. This is not actually part of this problem, but I just want to double check that this is our actual inverse. Notice when I wrote this out, I did not use the version of our inverse with the 1/10 distributed through because I just didn't want to. I think that the math is much easier without that. So I'll leave the 1/10 on the outside for right now. Now I'm a little bit concerned about that -18. Let me just double check. Yeah, you can see that -18 is incorrect. So we did a mistake somewhere. The 1/2 and the 3 actually do work out because that's what you would get if you were to multiply the 1/10 through. This would be a 1/2, this would be a 3. But this, I need it to be a -1. So there's something wrong in my arithmetic. And specifically, because it has to deal with this top row element right here, I know there's something up with that top row right there. Let me just double check that I copied everything okay. And let me make sure that I actually wrote out the minors okay. And I didn't. I could easily see right here. This is the mistake. 4 minus 4. I wrote that as a -8. It's actually a 0. So let me fix that. I like to keep it raw in here so you can see that I do actually make mistakes. So there we go. That should be a 0, which means this should be a 0, which means that this should be a 0. Quick fix. Luckily, I decided to check my work. Now if I double check here, that's -12 plus 0 plus 2 is -10, which is definitely correct, -1. There we go. Nice if you have the ability to check your work, but you can see a lot of places where arithmetic can bite you. So be very careful, and I'm okay with leaving that mistake in the video because, well, you have to see that mistakes can occur. And if you have an ability to check your work, I highly recommend it. All right, that's actually all I needed to do for this video. I don't want to prove the inverse via adjoint theorem. Not that it's hard to prove, but just because I'm running out of time, so I need to kind of get off this video. And also, I do proofs almost every single video. It'd be nice just to take a break. All right, I hope this video helps out with whatever you're learning in linear algebra, and I hope you have a great day. Be a good human.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.